distribution. I'm not in love with this problem. This problem's a little confusing, but I'm going to take my best shot at it. Okay, so let's take a look at this first part. What is the probability? The mean response time for an ambulance is 5.9 minutes. Okay, that's our mean. Our standard deviation for the response time is 1.1 minutes. So most of the response times are going to be clustered around 5.9 minutes. So what's the probability that the ambulance will take at most 7 minutes to respond to a call? Well, I'm going to sketch this out. Get my notebook up. Okay, so I'm going to just use either. You can ignore the comments up there at the top. I'm going to sketch this out. So we're saying that we're hoping that this distribution is basically approximately normal. Okay, so if I draw a normal distribution here, okay, the mean response time was, I think we said 5.9 minutes. And the standard deviation, okay, it's in community, maybe regarded as a random variable. Standard deviation is equal to 1.1 minutes. Standard deviation is equal to 1.1 minutes. And the mean is equal to 5.9. Now, based on what I've just written here, am I dealing with a population distribution or a sample distribution? Anybody want to tell me which one I'm working with here? There's kind of a dead giveaway on what I just wrote here. Right? Well, since I'm defining this as mu and sigma, I'm dealing with a population distribution, right? If I were dealing with a sample distribution, I would have called it X bar, and I would have called it standard deviation. Okay, so if I say mu, or let me give you an example. With mu and sigma, I'm talking about the entire population. In other words, as if we followed every response for this community for, say, an entire year or something like that. That would be the population of all the responses. Okay, not a sample. Okay, so let's see what we have here. The standard deviation was 1.1, and the mean is 5.9. We want to know what percentage was greater than or less than 7. At most 7 minutes. At most 7 minutes. So we're interested in what proportion of this population responses is going to be less than 7 minutes, or at most 7 minutes. So we're interested in this area from 7 minutes down. So we want to know what that area represents. We can determine how many standard deviations away from the mean 7 in. So z is going to be equal to, right? It's going to be equal to x minus mu over sigma. It's going to be equal to 7 minus 5.9 over 1.1. So that's going to be equal to 1, plus 1. Okay, so this is exactly a standard deviation of 1. Well, there's two ways I can solve this. One way is to use what we know about the shape and the distribution of a normal distribution, and say to ourselves, well, what percentage of the outcomes would we expect to be between -1 and +1 standard deviation? Well, we know that's going to be 68%, right? Well, if that's 68%, the mean, if it's a standard normal distribution, is symmetrical, the mean is going to cut that in half. So there'll be roughly 34% in this area between the mean and -1 standard deviation, and 34% between the mean and +1 standard deviation. And the area that's left up here is going to be 16%. Well, we're not interested in that 16%. We're interested in the area below here, right? So it's going to be 1 minus 16%, or 84%. So the probability that you would get a response in 7 minutes or less is going to be 0.84, or 84%. Now that's a rough estimate. If we wanted to really calculate it more accurately, probably more accurately, we would use our knowledge of the standard normal distribution and actually calculate what is the area associated with a z-score of +1. And one of the ways that we would do that is we would look up our z-table. Okay, and let me just pull it up here. And for a z-score of +1, okay, let's see, +1. Remember again, this table is designed so that whatever the z-score is, the area we're going to get from this table is going to be the area to the left of z. So a z-score of 1.00, and again, if we want 1.5, we would have gone, of course, we would have gone to 1.5, 1.0. If we wanted 1.55, it would have been 1.50 would be this area. 1.51 would be this area, and so on, just going up to the top here and coming down. So 1.55 would have been in this column, and it would have been 94% approximately. Okay, but we want 1.0, so it would be represented by an area of 84.13%, 0.8413. Okay, so 0.8413. So instead of leaving 16%, it's actually really 15. It's 15.87% or 0.1587 probability. Everybody comfortable with that? The other way I could do this is I could use Excel. Okay, and in Excel I could use a couple of functions. Oh, we don't need this. Okay, in Excel we could use a couple of functions here. We could use the standard normal distribution since we calculated z already and say equals norm s dist parentheses, and now it's asking me for the z-score. So z-score of +1 would represent an area to the left of that z-score of 0.8413, same number I got before. Another way I could use Excel is you could say equals norm, just norm dist, the normal distribution, parentheses, and it queries me about, well, what's the value you're interested in, x, and that was 7, comma, what's the mean for this population? It's 5.9. What is the standard deviation? 1.1. And cumulative in this case is always going to be true because we're always going to be looking for the area to the left, total area to the left of that value of 7, and we get the same answer also. In that case, it actually calculates, it bypasses the step of calculating the z-score. So everybody okay with that? So now let's take a look at what this second part of this problem asks. Okay, now the second part of this problem, now we were dealing with a population there because we were told that, this is the average for every response for the whole year. So it's the population of responses. If the ambulance makes 9, so let's say we don't have that information and we want to base it on a sample that we're going to take of a particular night that during the year when we're able to survey this ambulance service. If the ambulance service makes 9 responses on a given night, what's the probability that the mean response is greater than 7 minutes? Now, is this a population distribution we're dealing with or a sampling distribution? Anybody want to hazard a guess? Right, that's a sample distribution. Very good. By the way, I just want to point out to you, I noticed that a couple of you guys actually, you gave me the answers ahead of time, but I kept, like bumbling through it to make sure that we kept everybody up. By the way, while I'm at it, let me just make sure that I have everybody muted so we don't get a lot of crosstalk and stuff like that. Okay. Okay, so in that case, we're dealing with a sample distribution. So that's really all we asked there, because to be honest with you, the reason why that's all we asked, we didn't actually ask you to, we asked you what the probability is. We have a mean response greater than 7 minutes. And the first question we asked population distribution. In order to figure out this response to what's the probability that the mean response time for the mean true response time for the entire population is all of the responses during the entire year is greater than 7 minutes, we have to use something called the central limit theorem. Okay, and since that's not going to be on the test, I'm a little reluctant to really go into that. Did we cover that? I'm a little confused right now. We didn't start to cover the central limit theorem yet, did we? You guys remember it, that word being mentioned? Nope. Okay, we did not. I'm going to give you a preview of it. The way we're going to figure that out is that we're going to look at this as if we were talking about. We're going to look at this. Let's see. Okay, let's see. Let me get my notebook back. What the central limit theorem tells us is that if I take repeated samples of size 9, in this case we're dealing with a sample of size 9, from this population, where the mean is 5.9 and where the standard deviation for the population was 1.1, if I take repeated samples from that population, well, I would expect that when I take a sample from this population, my outcome is going to approximate the mean of the population in my sample. I'll be more likely to be close to the true mean if I take a big sample than if I take a small sample. Well, if I actually put together a distribution that represents all of the possible outcomes of sample size 9 in other words, we went back every night and sampled 9 results and then looked at the way the average for all of those nights would fall out, we would expect the mean for all of those to be the same, to be 5.9. In other words, half of the nights will underestimate the mean by taking a sample 9, half time will overestimate the mean. Now, the distribution of those results from the mean, instead of being spread out like the actual individual nights, since they're averaged over, it's an average of 9 numbers, we would expect that distribution to have the same mean, but to be narrower. So in that case, we use something called central limit theorem, and we'll learn about this next week. And what we can say there is that the standard deviation of our samples is going to be called standard error, and it's going to be equal to the standard deviation of the population divided by the square root of the sample size. So x bar, our mean, is going to be the same. It's going to be 5.9. Our standard error is going to be equal to 1.1 over the square root of the sample size, which is divided by 3. I'm just going to round this off. I'm going to say that this is roughly 0.4. So now when I look to see what the z-score is for a value of 7, right? Well, in that case, the area I'm looking at now, the z-score for that 7, instead of being it's 7 minus 5.9 is equal to 1.1 divided by sigma. Well, sigma is going to be equal to 1/3 of that. So instead of being 1.1, it's going to be roughly a z-score of 3. So this area now is going to be much smaller, and the area that we would measure from our z-table would be much larger. This might be as small as only 0.001. Okay, so don't worry about that. It's not going to be on the test. So I'll get off of that topic right now. Okay, so let me go back over the rest of the questions on that that are actually relevant to what we're doing. If I can find it again. There we go. Okay, let me blow it up a little bit. Make it a little easier to see. Okay, device measures blood pressure. Now I just want to, if we go back over the homeworks, let me pull up the homeworks. Just going over them topic by topic. You can pretty much assume that one of the things that you're going to see, let me see if it'll let me open this. One of the things that you're likely to see is some questions that ask you to identify variable types. What kind of variables are nominal variables? What kind of variables are ordinal variables? What kind of variables are numerical variables? I don't want to get into too much of the idea of discrete variables because they're running on numerical variables also. Hopefully we won't play around with that too much. Okay, in addition to that, you're likely to see something that involves the use of a graph or a table. In fact, in our practice example, there is one. So when we go back to that, I'll go over that. So you can almost certainly see some sort of table like that precedence table, a histogram, a summary of data like a histogram, where we'll ask you some questions about, ask you to interpret that histogram. And like I said, we'll go back to that momentarily. It's likely that you'll be asked to do some basic statistical calculations, descriptive statistics for numerical variables, mean, standard deviation, minimum, maximum range, and so on and so forth, and perhaps also even percentiles. Okay, now, like it's likely that will give you the choice to use Excel or SPSS rather than force you into using a particular way of doing it. However, there may be an instance where you'll need to use SPSS to make it practical. For instance, if we ask you to produce a box plot, and a box plot is produced in SPSS in moments, where it would take you a while to do the calculations in Excel and then to draw it out and so on and so forth. So it's practical to figure that you're going to do that in SPSS. Okay, so there's a couple of questions in SPSS, similar to homework that you might run into. Okay, let me go to the next homework. Okay, I think I can go in here. Okay, and the second homework, we're looking at probability and diagnostic testing. Okay, with probability and diagnostic testing, it's likely we'll ask you some simple questions about that might involve the multiplication rule, such as what if you get all the same outcome to predict a certain outcome for a certain number, sample of a certain size. For instance, if the probability in a population of HIV, or the prevalence of HIV is 7%, what's the probability that if you randomly select 4 people from that population that they'll all have HIV, or none of them will have HIV? And of course, that would be 0.07 times 0.07 times 0.07, 0.07, or the converse would be 0.93 times 0.93 times 0.93, and so on. Okay, so you might see a question like that, and you've already seen some of that. We've given you a pretty exhaustive group on the assignment and in the PowerPoints of some of the interpretations of the Venn diagrams. So you might want to brush up on that because you might see them as well. And then you might actually see some tables that give you a result for the application of a diagnostic test. And of course, in a situation like this, what are you likely to be asked? You're likely to be asked what the sensitivity of the test is. Like in this test, the sensitivity, 100 people have the condition. It correctly tests positive for 80 people out of 100. So the sensitivity of this test is 80%. What's the specificity of this test? Well, out of 900 people that don't have the condition, it gets it right 810 times. 810 over 900 is 90%. So the sensitivity is 90%. And the positive predictive value. Anybody want to tell me what the positive predictive value would be for this particular case, real quickly? The positive predictive value is going to be the percentage of the time that a positive result means that you actually have the disease. So how many people test positive in this population? Right, 170. Yeah, there you go. And since only 80 of those 170 actually have the disease, then the positive predictive value is 80 over 170. Or even if you test positive, likelihood of you're having disease is only, as Jaya says, 47%. Okay, so I would be prepared to, take a look at some of that. Negative predictive value is, of course, in this case, going to be 20 over 830. Now, you may not get the data presented in exactly this manner. You may instead only be presented with the sensitivity, the prevalence, and the specificity of the test, and for that, the prevalence of the disease in the population, and the sensitivity and specificity of the test, and asked to give us the positive predictive value. And we know that the positive predictive value is a conditional probability, where A is the probability that you have the disease, and B is the probability that you test positive. So P given a probability of A given that B has occurred. In other words, a probability that you have the disease given that you tested positive, B, is the positive predictive value, just as we calculated it up here. And we can calculate that using Bayes' theorem, which is where this formula is derived from. Okay, so if you can work this out from those 3 numbers, it's basically math from that point on. So I don't want to beat this to death since we don't have that much time. There's also in the example that I gave you, there's also an opportunity to play around with that as well. Okay, and let me see what else we got here. I don't want to close tabs. I want to go back here or here. And let's see, binomial distribution. You know, this caused a lot of, binomial distribution, I noticed, caused a bit of an issue with a lot of people because it's a little bit hard to interpret. Now, remember that the example I just gave you of a situation where we're talking about a population where the prevalence of HIV is 7%. I asked you, what's the probability that if you chose 4 people randomly from that population, that all 4 are HIV positive? Or conversely, what's the probability all 4 are HIV negative? Well, that's an easy thing to predict. There's only one way to have that outcome, for each person to be positive or for each of the 4 people to be negative. So the probability of all of them being either way is going to be whatever probability you're dealing with times itself 4 times. 0.07 times 0.07 times 0.0, and so on. Well, what if I asked you, what's the probability in that same population that if you randomly take 4 people from that population, that only 2 of the 4 are HIV positive, or exactly 2 of the 4 are HIV positive? Well, that gets a lot more complicated now, because first you pick out one person, that person could be positive or they could be negative. Second person could be positive or negative. The third person similarly could be different. So you could get 2 out of 4 many ways. The first and third person could be positive, the second and fourth, the first and fourth, many different ways of having that outcome out of all the different possibilities that you have. So in that case, we apply the binomial distribution. We apply in our case, for the most part, that usually means applying a function in Excel that helps us to calculate those probabilities. And I'm going to do that right now. So the way binomial distribution is going to work for us is I'm going to use, first of all, it's called binom dist. And I'm going to put in a couple of parentheses there. And inside of those parentheses, we're going to tell Excel certain conditions about the probabilities that we're dealing with and the conditions that we're interested in. The first thing I'm going to tell it is, well, I'll tell you what, I'm going to tell it a number of things. The first thing I'm going to tell it is the number of successes. And I'll define that in a second. Second thing I'm going to tell it is the number of trials. The third thing I'm going to tell it is the probability. And the fourth thing I'm going to tell it is true or false for cumulative. Okay, I'll type that in as cumulative, which is basically an answer that is true or false. So what do we mean by successes? By successes, we mean that if your trials are the number of people that you sample randomly. So for instance, here's our population. Our probability of being HIV positive is 0.07. We're going to sample 10 people. So our trials is a sample size of 10 people that I'm going to pick randomly. Okay, and each one of them has a probability of 7% chance of having HIV, of being HIV positive. Okay, so now let's say that I'm interested in the outcome where the number of people that actually have it out of 10 people is 2. I want to know what's the probability of getting exactly 2 out of those 10 people that have HIV. So 2 out of 10. 2 is the number of successes out of 10 trials that I'm looking for, and that's the probability of that particular outcome, or of any single outcome. Okay, so let me calculate that right now. Equals binom dist parentheses, and I'm going to put in, see, it prompts me, number of successes is 2, 10, 0.07. Now, at this point, I'm going to type in either true or false for cumulative. I'm going to type in false. What false tells me is I want to know exactly the probability of that outcome. I don't care about 1 out of 10, none out of 10, 3 out of 10. I want to know what's the probability of getting exactly 2 people. So for cumulative, I put false. And it gives me that probability. It's 12% chance of having that exact outcome. Now, the difference with when I'm looking at the situation where I might ask you, what's the probability that 2 or fewer people in that sample of 10 people have HIV? What's the probability of that outcome? Let's take a look at that. Binomial dist. Now, what's the number of successes? Well, it's 2 or fewer, comma, 10, comma, 0.07, same as before, except this time I'll say true. And what Excel is going to return now is the probability of getting exactly 2 people out of 10 that are HIV positive. But also, since I said true for cumulative, it will include the probability of anything less than that, 2, 1, or 0. So it's the cumulative probability for all of those outcomes from 2, 1, or 0. So that's more likely, obviously, than having just an outcome of exactly 2 people, right? So our probability of that outcome is 97%, which isn't so surprising because the most likely outcome is probably 1 or none, because the probability is only about a little less than 10% out of 10. Probably the most likely outcome would be 1, which was not in exactly 2. Okay, so you guys comfortable with that? You could do this calculation if you needed to. Give me a little bit of feedback if I need to kind of beat this to death a little bit more. So hopefully, it'll be straightforward enough that you guys will figure it out. I just want to ask you one more thing. What's the probability of getting 3 or more people that are HIV positive? So maybe one of you can tell me how I might do that. It's pretty simple once you've done this. It's the probability of 3 or more people out of 10 would be HIV positive. If I don't get a response in a second, I'll go ahead. Right, exactly right. Thank you very much, Jermaine. We already calculated the probability of 2 or less is 97%. So yeah, 1 minus exactly, you could do it exactly that way. Okay, so the probability is 97% that you would have 2 or fewer. So the probability that you would have 3 or more is what's left, or 3%. Okay, since that's exhaustive, you got to have either fewer or more, one or the other. Okay, good, excellent. So, and again, that's most of that. I think you get through most of that pretty well. And the other thing that we covered was the normal distribution itself. And in the normal distribution, we just had that example that we worked out, and I gave you a few more in the example that questions that I put up there before as well. So let's go back to those questions now. Okay, and let me see if I can get back to that. Let me close these tabs for now. Lead page, good. Okay, let's take a look at this. Let's take a look at some of these problems. Go through them very quickly. Device that measures blood pressure correctly identifies 85% of hypertensive individuals. So our sensitivity is 85%. It incorrectly identifies 10% of the normointensive individuals as being hypertensive. So it predicts that people are not hypertensive are 10% of the time. So we have a test that has a sensitivity of 85% and a specificity of 90%. Gets it right 90% of the time if you don't have high blood pressure. Okay, so assume that 20% of the test population is hypersensitive. Now, I constructed this table. Sometimes if you don't remember how to use Bayes' theorem, sometimes you can kind of beat this whole thing by constructing your own little crosstabs table. Okay, and how did I do that? I said, okay, let's take a population of 1,000 people. We know that if we have 1,000 people randomly chosen in this population, or if the entire population is 1,000 people, we know that the rate of hypertension is 20%. So out of those 1,000 people, 200 of those people would be hypertense. 800 would not be hypertense. Well, out of those 200 people that are hypertense, our test would correctly identify them 85% of the time. So we would correctly predict that 170 out of 200 people that have the disease test positive, and 30 of those, 15% of them, test negative. That's, in other words, that's a false negative. They really are positive. It's false negative. Just to point out, this is a true positive. This is a false negative, right? Because it's a negative. This is a true negative, and this is a false positive. Okay, so now what about the 800 people that don't have the disease? Well, we get that right 90% of the time. So 720 out of those would be correctly identified as being negative, and 80 would be incorrectly identified as being positive. So if we look at this, we've reconstructed this table just from the information we had above. And now I can see that the total number of people out of 1,000 that test positive is 250. And the percentage of those that actually have the disease out of 250 is 170 over 250, or our positive predictive value. And the percentage of them that don't have the disease, test negative when they don't have the disease, in other words, a negative predictive value, is 720 over 750. Okay, so we can deduce that if we forget about our other, if we don't want to apply our formula where we're given the sensitivity and specificity and the prevalence. If we don't want to apply that formula, we can kind of work our way around that, can't we? Okay, but it's good you might want to practice that again with these. Since you know what the outcome is here, you could go back and try this with this formula and see if you get the same result to make sure you know how to apply it. Okay, so patient test positive. Okay, this I think it gives you a few examples of this. Increases sensitivity. Okay, so now you might get some word problems on here. Like, for instance, what are some ways to increase the positive predictive value of the test, right? Well, you could increase the sensitivity of the test, right? But even if you increase the sensitivity of the test, right, you'll still get some people that are negative that test positive, right? Even if you have 100% sensitivity, because if the specificity is 100%, then some people that are negative will wind up appearing to be positive. You can increase the specificity, but you'll be missing some people if you increase the specificity. You'll have a better positive predictive value, but you may miss some people if you don't increase the sensitivity because they'll test false negative. Okay, and applied it now we know that the positive predictive value goes down if you're testing a disease, if you're using the test in a disease that has a low prevalence. Why does it go down? Anybody want to suggest a reason why? If I gave you if I gave you a test that had a sensitivity of 90%, specificity of 90%, that the which population? Let me back up. I have a test has a sensitivity of 90%, a specificity of 90%. I have a population, two populations, one with a prevalence of 10% and the other with a prevalence of 1%. If I apply the same test to those two populations, which of the two populations will demonstrate a higher positive predictive value? Which one of those two populations, the 10% prevalence or the 1% prevalence, for the same test will give me a higher positive predictive value? Somebody take a guess? Right, the one with 10%. The one with the lower prevalence is going to give us a lower positive predictive value. Well, why is that? Because you're applying the same test to a population that has more people that don't have the disease. And since that's the case, and your specificity is the same in both tests, you're going to get more false positives from the people that don't have the disease, simply because there's more people that don't have the disease. So if you apply the same test to a population with a lower prevalence, you're going to get a lower positive predictive value. You're going to have more people that are false positives than you would in a higher prevalence situation. Okay, so keep that in mind. You might get some questions like that when you see the exam. Let me get this out of the way. Let me go back to this other one. Okay, so let's see. Okay, let's go back here. So let's take a look at this chart. Okay, and again, there's some examples of different kinds of variables. Here's our chart, emergency clinic, at least one patient treated every day. Okay, okay, let me look at this one. It's a little bit simpler, I guess. Well, let's see what this says. Emergency clinic, 30 days, number of days, patients arriving between 12 and at least one patient was treated every day. This produced a list of 30 numbers. Okay, it's the number of patients that came in the morning. Each number represents number of patients treated on the night shift that day, 12 a.m. 7. Below is a histogram of data on how many days are there more than 8 patients treated in the emergency clinic. Well, how many days have more than 8 patients that are clean? So this is the number of patients. So this is 8 patients treated per day, 9 patients treated per day, 10, 11, 12, 13. There's only one day where 13 patients were treated on that day. There's only one day with 12 or 11. There are 3 days where 10 patients were treated, 3 days where 9 patients were treated, and 3 days where 8 patients were treated. So how many days were more than 8 patients? Well, I don't want 8. It says more than 8. So it would be 3 plus 3 is 6, and another 3 is 9. There were 9 days out of 30 where you had more than 8 patients that came into the emergency room. Okay, if I look at the chart below, what's the percentage of individuals that weigh more than 140 pounds? Okay, there's 50 people. It's supposedly 50 people here, I guess. That must be 10. Let me. Body weight of 50 individuals. You could actually count these to see if there's really 50 there. I'm going to take it at its word. Okay, so what's the probability that what percentage of individuals weigh more than 140 pounds? Well, here's 140 pounds. This is not a very good chart, is it? Right? So the percentage of people who weigh more than 140 pounds are the people that are in these two histogram bars. Okay, and that would be 7 people, and looks like 5 people. 7 and 5 is 12 people. That's 12 people out of 50 people, right? Is going to be 24% of this population. Hang on, let me think about that a second. 7 and 5 is 12 out of 50. Yeah, 24% of this population weighs over 100. Did I do that right? 12. Yeah, 24% of the population weighs over 140 pounds. You can actually go back and actually count, see if there's really, see if there's a really 4. That's 8. That's 10, 18, and 3, 21, and 9. It looks like 10, 21, 31. Oh, maybe that's 30. That's 9, 30, 30, 38, and 12, 50. There are really 50 there. Okay, so that'd give you an idea how you might work that out. Now, what if I asked you that given, let's go back up here. Let's stay here. Given that a person weighs over 130 pounds, what's the likelihood that they would weigh over 140 pounds? Well, that's a conditional probability. The first condition is given that the person weighs more than 130 pounds. So we're only concerned with the people to the right of 130. How many people is that? That's 4, 8, and 12 is 20 people, right? And what's the probability that those 20 people that they would weigh more than 140 pounds? Well, there's 12 people weigh more than 140 pounds. So 12 out of 20, right, is going to be 60%, I guess, right? Would be 60% of the people. The probability is 60%. Okay, studying hard to calculate mean. Now you have a list of numbers. a mean and median heart rate for the first 5 patients. Okay, so let's see. Heart rates of 5 patients, 150, 40, 120, 104. Calculate the mean and median heart rates for these first 5 patients. Of course, the mean, we would find the average. The median would be the middle number. The middle number in this case looks to be, just off the top of my head, 120. Okay, that's the median. That's the median. We will also have a mean. Discovering that the second patient's rate was misrecorded and should have been 140 instead of 40. That makes it 140. Recalculate both the median and mean and median of the corrected data. Okay, so does this mistake have a greater impact on the mean or the median? Well, if this is now 140, let's see, you can actually calculate it if you want. I predict that the median is not going to change much. It's going to wind up being, let's see, 120, I guess, instead of 104. So it's only going to change a little, but the average probably will have a greater change. The mean tends to be more sensitive to outliers than the median is in general. Okay, Federal Reserve, 4,000, excluding 70 outliers, extremely what they sample 4,000 households, estimated overall net value of family, excluding some of the outliers, extremely wealthy individuals. The report summarized 44, excluding outliers. They reported the summary is 44,000, and one of these was the mean and the other was the median. Which one of these do you think was the mean income and which was the median income? Anybody want to take a wild guess here? I would think this would probably be the median, right? Because you would think that if you're going to have some people that have very high incomes, right, that are going to pull the mean upwards, where the median would actually represent the middle value for all of these, all of the different values. Yeah, I would predict that that's the mean, and this is the median as well. Okay, let me see if I can't find suppose that 3% of the people in the given community, adults, have attempted suicide. Suppose it is known that 20% of the community are living below the poverty level. If these two events are independent, what is the probability that a person selected at random from this community will have attempted suicide and be living below the poverty level? Okay, so now these are independent events, right? So if they're independent events, that means that there's no association between one and the other necessarily, right? It's going to be the probability of A times the probability of B, okay, which is 3% times 20%. Okay, now what if I told you that in fact, what would that be? That would be 0.03 times 0.2 would be, let's see, I'm going to pull up Excel again just so we have it. Okay, so that's going to be equal to 0.03 times 0.2. So the probability that any individual you chose from this population would be living below the poverty level and have attempted suicide is about 0.6%, 0.006. Now, what if I told you that we did a study and we sampled a large portion of this population, and we found that the probability of someone having, in this same population, where we know that it's 3% rate of suicide, prevalence suicide is 3%, attempt suicide is 3%, and the poverty level is 20% in the same population. And I told you that the probability, based on our study, that a person would be both have live in poverty and have attempted suicide, that probability is actually 0.12. What would you tell me about those? What would that tell us about this? These two variables, whether or not someone attempted suicide or lived at the poverty below the poverty level. If it came out to be, if I actually counted it, did a survey and it turned out to be 1.2% instead of 0.006%, that you would have both of those conditions. That they're not independent. Exactly right. If it doesn't come out that with this result by multiplying the two probabilities indicating that they're independent, if it doesn't come out that way, it would suggest that they're not independent. That it say, for instance, in this case, that a person that's living below the poverty level is more likely to have a attempted suicide than a person not living below the poverty level, or vice versa, for that matter. Okay, so you might see something on a test like that. You might get a little curve where it might ask you to make a judgment like that. Further table below, a proportion of women made more than one visit to an obstetrician's office during a uncomplicated pregnancy. Well, let's see, what proportion of women made more than one visit? Well, 2% made less than one visit. That 20% made no visits. 20% made one visit. So the percentage that made more than one visit is 50% had two and 10% had three. So 60% of this population. Okay, now that might be complicated by a question like, given that someone has made a woman in this population has visited the obstetrician's office, what's the probability that they went 3 times or more? Okay, you guys want to tell me what that might be? Given that you know that the person, conditional probability, given that the woman has visited her obstetrician, what's the probability that she went 3 or more times? Okay. It looks like 10%, doesn't it? It's the probability that any woman in this population, even the ones that didn't visit their obstetrician, visited 3 times, is 10%. Given that she saw her obstetrician at all, what's the probability that she went 3 times? Well, these don't count since they don't meet our condition. Okay, given that she visited the obstetrician at all. Okay, so we're only interested in these probabilities, 20%, 50%, and 10%. So given that she's among these women, what's the probability that she went 3 times? Well, it's going to be 0.01 over 0.08. Okay, and you can figure that out. That's going to be, I think, 0.125. It's going to be 12.5% rather than 10%. Does that make sense to you, Jaya? See, there was because a little bit of a trick. That's why I want you to keep your eye open on these things, because occasionally you might get a little bit of a twist, or a little curveball on these things. An infinite psychomotor development index, an infinite selected at random probability that the infant's PDI score. Now the mean is 100, standard deviation. The probability that the infant's PDI score exceeds 103. Well, unfortunately, I can see right away that 103 is 3 above the, is 3 above 100, the mean, and the standard deviation is 15. So my z-score for 103 is not going to be an even number like one standard deviation above or one standard deviation below. So I'm going to have to use my z-table to calculate that. Also, find the probability that they're between 97 and 103. And find a z-score for a probability of 90. Would you be surprised to observe a value of 90? So let's sketch that out. Let's do this one. Okay, now then we'll call it a night. And hopefully, if you guys email me some problems or some issues and stuff like that, I'll do some written or maybe even tape a video of some solutions or something like that. So let me go back here and draw this. So here's my normal distribution. Okay, not very well drawn. And it was mean was 100. Mean was 100. The standard deviation was equal to 15. And we were interested in 103 and 97. So the first thing we got asked was, what's the probability that an infant's PDI score exceeds 103? So the area we're interested in is the area, remember this is our mean, I'll make it a little bit darker. So we can distinguish it from the two numbers that we're interested in. So we're interested in what's the probability that a infant would be in this portion of the population. Well, I'm going to calculate my z-score for 103. It's going to be 103 minus 100 over 15, and z is equal to 3 over 15, which is 1 over 5, which is 0.2. Right? Z-score is going to be equal to positive 0.2. So my tables do not give me the area to the right. They only give me the area to the left from here down. So I'm going to call up my z-table. Okay, here's my z-table. So positive 0.3. 0.0 was, or 0.02, was it 0.02? 0.2. 0.2, positive 0.2 is 57.93. I'm going to call that for our purposes 58%. So the area to the left here, of here is 58.58 or 58%. So that leaves the area above 103 to be 0.42, the area under this curve. So that represents the percentage of this population that are above a score of 103. You could also look at it as the probability, if you selected a single individual from this population, that they would have a score above 103. Okay, so my probability is 103. So the next question was, well, what's the probability that you would have a score between 97 and 103? Well, let's see. This area down is 0.58. So what about 97? What's the z-score for 97? Z-score for 97 is 97 minus 100 over 15, x minus mu over standard deviation is minus 3 over 15, is minus 0.2. Right, so minus 0.2. Let's go back to my table. And I'm looking for the area to the left of, okay, and I have to go to the negative table, negative 0.02, and that is, I'm going to round this off for our purposes, I can do this quickly, is negative 0.38. So let's go back here, and that's going to be negative 0.38 is the area to the left of 97. Okay, so now I'm interested in the area between 97 and 103, the probability of choosing an infant that has a PDI between 97 and 103. So I need that area. There's a couple of ways that I could do that. One way is I could just say, well, this is 58% from here down. And if I subtract 38%, it leaves me the difference, or in other words, 20%. Probability is 0.20. The other way I could do this is say, oh, well, this area from here down is 38%, and I previously calculated the area above here is 42%. Add them together, that's 80%, and what's left is the area in here, or 20%. So either way, this will work out for us. Okay, so you're going to have a number of problems. Now, I suggest that you consider actually drawing out the normal distribution. I know you're going to be tempted to just do it on the fly, especially if you have to do it a number of times during the test, or you have to do it several times during the test. But you can really avoid making some errors if you actually kind of just sketch it out to make sure that things look the way that they should. Now, there is one last thing that I want to mention here. What if I asked you, I want to know what PDI score would represent the bottom 10% of these infants? In other words, what PDI score would you have to be below in order to represent the bottom 10% of these infants? Okay, well, in that case, we know what the area we want is, but we don't know what the value is. What is that score? Is that score 95? Is that score 90? What is that value that we're interested in there? Okay, well, what I can do there is I can use my Agrestes table to find the z-score for that area. Let's bring this up here, and we know that these numbers in the middle here represent the areas. The numbers on the left and the top represent the z-score. So if I go in here, see, if I were looking for an area of 80%, I would go to the top. And I would know my z-score is going to be, say, for 80%, is going to be like here, right? Positive 0.88 is my z-score. But in this case, I'm looking for 10%. So let's find 10%, area of 10%. An area of 10% is represented by a z-score of, let's see, 0.98. Where am I? 0.96. 985. It looks like this is the closest, and that is 0.128. Negative 0.128. Z-score of negative 0.128 represents an area to the left of that of 10%. So I know that the z-score of that value, which represents the bottom 10%, is equal to negative 1.28. So now what is the number? What's the PDI score that represents? Remember that formula? Z is equal to X minus the mean over the standard deviation. Well, in this case, we know what Z is, minus 1.28. We know what mu is 100. We know what sigma is 15. The only thing we don't know is what X is, X minus 100. So since we have a formula and we only have one unknown, we can actually solve for this. So if I want to go ahead and solve for this, I'm gonna cross multiply. It's gonna come out to be minus 1.28 times 15, right, is equal to X minus 100. Right, I'm gonna move the 100 over to the other side. So X is gonna be equal to, I'll just switch sides here. X is going to be equal to 100 minus 1.28 times 15. Okay, and what's that going to be equal to? That's going to be equal to 10%. 80.8. Okay, somebody saved me the trouble of actually calculating it out. I appreciate that. Okay, so and in fact, you could see that if you did that backwards, you'd get the same result. In other words, if you calculated, is that right? I guess that is right? Yeah. And let me just see, 1.28, 90%. Did I have that right now? Let me just make sure I got the right number there. That does sound right. That does sound right to me. Bottom 10%, 1.28. Okay, standard deviation. Yep, that looks right to me. So if you want, you could work that backwards. In other words, you could check yourself by saying, well, if the z-score is 80.8, does that really represent, I mean, if the value of the PDI is 80.8, 81, let's say, does that represent really the bottom 10%? You can do that by starting with 80.8, calculating what the z-score is for 80.8, comes out to 1.28, because you're just going to divide the difference between that and the mean by 15, just the opposite of what you did before. And then it's going to come out to 1.28, and you're going to look up 1.28, and you'll find that it's negative 1.28. You'll find that it represents an area of 10% to the left of that value. Okay, so you might see, there's a little curve that you might see on the exam as well. Okay, so let's call it a night. I'll post this, even with my slight ramblings at the beginning. I'll post this later on, so you'll be able to go back to it if you need it. And please take advantage of me if you want to. Two things. I set up the discussion board on Blackboard, so you guys can answer each other's questions. If I can't get to them, you might be able to answer each other's questions before I can get to them myself. So post questions or issues that you might have, or things you don't understand, on the discussion board on Blackboard. Create a new thread, and we can answer the question. You or your fellow students can answer the questions for each other. Or if you prefer, you can email me, and if I know what the question is, I'll post some sort of answer to it or something like that if you have any other questions. Okay, so good luck on the test, and I'll see you on Thursday night. Okay, if I don't hear from you by email or something like that before. Bye.